carry forward with this model and start to think about things like computational complexity. Here we're dealing with relatively small objects with not a lot of possible state values. You know, genetic state, it's only got 3 possible values of its different states. But the principles here of seeing how information graph structure turns into computational complexity is an important issue that we're going to be making quite a lot of use in our subsequent topics. So I'd like to work through an example of this. So we're just going to start from the information graph structures that we just worked out for the DAD model on the left and the not DAD model on the right. And the basic challenge to you here is to turn these information graph structures into equations for the joint probability of our observables given our root variable theta. In other words, probability of MCS given theta. So write an equation for probability of MCS given theta for each of these 2 information graph structures. And second, state based upon the factoring of that joint probability, if it can be factored at all, what the computational complexity for actually calculating that joint probability would be. And in the usual way, let's state our computational complexity in big O notation. In other words, let's just abstract the number of possible states of our hidden variables. Let's just assume they all have the same number of possible states for each random variable, hidden variable, and we're just going to call that number of states for those hidden variables, we'll just call that n. So we're going to give it as some big O notation for n. Okay? Any questions about what you're being asked here? Okay, well, so write an equation for the joint probability MCS given theta, and indicate with parentheses how you think it factors, if it factors at all, and then give the big O notation in terms of n for the computational complexity on calculating PMCS given theta for those 2 distinct models. Question?
How to measure the computational complexity?
Right, so I was basically saying in terms of n. So in this case, n equals 3, right? Because our hidden variable, like kappa, it has 3 possible hidden states, right?
Yes.
Yeah, so I'm just saying write it in sort of an abstract, standard big O form. So instead of, you know, actual numbers, let's use n. In this case, it so happens n equals 3, which of course is pretty trivial, but let's keep it in terms of the abstract using n, okay? So it might be something like, you know, order n squared or whatever it is.
Yeah, I see.
Thanks for the question.